Greetings everyone. In this video we are going to talk about magic methods in Python. Magic methods, also known as Dunder methods, which are the double underscore methods. They are special methods in Python that have double underscores at the beginning and end of their names. These methods provide a way to define how objects of a class behave in various contexts, such as arithmetic operations, string representations, comparisons, and more. They allow us to customize and enhance behavior of our classes, making them more intuitive and user-friendly. There are many magic methods, such as init, the constructor method, called when an object is created. In addition, a string, called the string function to provide a human-readable string representation of the object. Also, addition, called when the plus operator is used between objects. In addition, subtraction, called when the minus operator is used between objects. In addition, pick, or equality, called when the double equal sign is used for equality comparison. In addition, less than, called when the less than operator is used for comparison. Also, length function, called by the length function to provide the length of the object. These are just a few examples of the many magic methods available in Python. Let's make an example to understand. Imagine if we needed to perform mathematical operations on polynomial objects in Python. This could be useful in various scenarios such as algebraic computations, scientific computing, and data analysis. In this example, we'll create a polynomial class that allows us to define and manipulate polynomials. We'll implement special methods like add for addition and multiple multiplication to perform arithmetic operations on polynomial objects. Let's dive into the code. Firstly, let's create our class. And then let's define the initialization method to initialize the polynomial objects with its coefficients. Next, let's implement the addition magic method to add two polynomial objects together. Def add self and other. Here, self refers to the current instance of the polynomial class, which represents the first polynomial object involved in the addition operation, and for other, it represents the second polynomial object that we want to add to the current polynomial object self. A plus B for A and B, zip, self.coefficient, and other coefficients. And then return for the polynomial coefficient. Inside this method, we perform the element-wise addition of the coefficients of the current polynomial, self coefficients, and the other polynomial other dot coefficients. We used the zip function to pair corresponding coefficients from both polynomials, then add them together using a list comprehension. The result is a new list of coefficients for the sum of the two polynomials, stored in new coefficients. We then create a new polynomial object with these coefficients and return it as a result of the addition operation. More or less the same idea for multiplication. Solve under. Here we also did the same, but instead of addition, we did multiplication. So A multiplied by B for A and B in the self-coefficients and other coefficients. Now imagine we're working with polynomial expressions, and we want a convenient way to represent them as strings. For example, we want to be able to convert a polynomial like 3x to the power of 2 minus 2x plus 1 into a readable string format. To achieve this, we define a special method called string. In Python, this method is automatically invoked when we try to convert an object into a string, such as when we use print. So, def str or string self return to join coefficient index coefficient in the rate, so coefficient minus 1. Now let's break down of what this method does. Enumerate self-coefficients. This part reverses the list of coefficients and then pairs each coefficient with its corresponding index using enumerate function. Then double colon minus 1. This part reverses the list because when we write a polynomial, we usually start with the highest degree term first. And then the if string coef x to the power of index for index and coefficient, with the list comprehension that creates a string representation for each term of the polynomial. For example, if the coefficient is 3 and the index is 2, it would create the string of 3x to the power of 2. And then joint method. It is used to concatenate all of the strings representing the polynomial terms, separated by plus sign, to form the final string representation of the polynomial. So when we call print on the polynomial object, this method formats the polynomial as a string with each term separated by plus sign. For example, if self-coefficients is 3 minus 2 and 1, the output might be 3x to the power of 2 plus minus 2x to the power of 1 plus 1x to the power of 0. And now let's implement the length method. Def length, so return length self.coefficient. And then we go for the equality comparison. So def if self and other. In return self-coefficients put other dot coefficients. Then we go for the subtraction. So def sub self and other coefficients equals to a minus b, where a and b zip self coefficients the other dot coefficients. Sure, any. And now let's create our two polynomials. So poly1 equals to 0, and then 3 minus 2 and 1. Only 2 correct 0. This 0 iterations. print build one, polygon, and then let's make addition. So underscore sum polygon plus print side sum polygon scroll down polygon times polygon, right? Or finish it poly blah. That also poly swap to polygon minus poly2 print so so and to print is a string representation of the polynomial that string poly1, and to print the length of the polynomial print del poly1. And finally, to check the equality of the two polynomials, print poly1 equal x1 poly2. In this case, it will print true if the two polynomials have the same coefficients and false otherwise. Let's add here string, give us our string, and here nice pronunciation here. No, then the stop here. Now let's check, and here we have it. We firstly got polynomial 1, and then polynomial 2, and then the sum, multiplication of the two polynomials, subtraction, string, length, and equality. For equality, we know both are not equal, so we got false. And for the length of polynomial 1, it contains 3 numbers, so we got length equals 3. And regarding for the string, this is the string of our polynomial. And for subtraction, we got polynomial 1 minus polynomial 2, and we got 5 minus 3 and minus 1. Let's check polynomial 1, which is 3 minus polynomial 2. So 3 minus 2 equal 5. So regarding the equality, length, string, subtraction, they all make sense. But while for multiplication and sum, we got these equations. Certainly, when we use the polynomial constructor inside the add and the mul methods here, polynomial, new coefficient in mul, and for addition also polynomial, new coefficient. It ensures that the result is returned as a new polynomial object. This is consistent with how these operations should behave for polynomial equations. So what will happen if we delete polynomial? Let's try to delete polynomial here in addition. And let's delete it in multiplication also. Now let's run our code. We got for sum 1 minus 1 and 3. So 3 plus -2 equal +1, -2 plus 1 equal -1, 1 plus 2 equal 3. Removing the polynomial constructor from new coefficients means that instead returning a new polynomial object, we're returning a simple list of coefficients. This changes the behavior of the operations, causing the result to be printed differently. In Python, the positive and multiplication operators between objects typically invoke the addition and mul methods respectively. By keeping the polynomial constructor, we're ensuring that these methods return a polynomial object with the correct behavior, representing the result as a polynomial equation. So if we want the result to be treated as polynomial equation, it's best to keep the polynomial constructor to maintain consistency and clarity in the code. Thanks for watching. I hope you enjoyed the video. If yes, then please don't forget to subscribe to our channel and hit the like button. Until next time, happy analyzing.